Hey gang, DSSS has had its heyday and it's gone at this point. It's pretty much been phased out. What do we use instead? OFDM, Orthogonal Frequency Division Multiplexing. What does that mean? Well, it means that we're going to multiplex a bunch of tiny little, just a little over 300 kilohertz sub-carriers within our overall channel. So kind of like DSS, but constructed differently because in addition to carrying data, we also have some pilot subcarriers that are here to manage synchronization and tracking to make sure that our signal is clean, that we're at the right place within our signal, that things are being sent correctly, kind of checksum values that are sent specifically over these channels. And then we have null power values that are sent over certain channels that are used as buffer areas in order to have our signals next to each other. And in fact, when we have multiple channels, you've got your 802.11a, I've got my 802.11a, what keeps them on different channels from overlapping to each other, even though they are butted right next to each other? Some of it is the no power subcarriers on the edge. Some of it is also the fact that OFDM actually is reading the magnetic degree of what's going on in addition to the electrical current. So it's a very three-dimensional wave that it's measuring. When we think about the modulations and the way that it measures signal, it is very similar to what we saw in our DSSS environment. It's just binary phase shift keying and the quadrature phase shift keying. But instead of it being based upon as you see a 1, flip the bit, a 0, keep it the same. That was what we saw in the binary with BPSK. In this mode, it's if it stays the same, keep it the same. If it flips, flip the bit. So a 1 is what is coming in. The next bit, why is it a 1? Well, because nothing changed. So therefore, we keep having a 1. Here we see, notice we were going up and then suddenly we're going back down. We flipped 180 degrees in our phase, so therefore the next bit's a 0. Oh, we flipped our phase again, so the next bit's a 1. Here we're coming down, then we come back up. Gang, should this be a 0? It shouldn't, should it? Now, this one's a small error in the slide, but it's good we could catch it. If our wave stays the same, then when we're using BPSK, we're going to stay with whatever we were using before, which was a 1. And the same thing here. We're not changing our wave, so this will stay a 1. Okay, good job. So now let's take a look at what's up here. Again, our quadrature phase shift keying. Again, the change in shifts is associated with a 2-digit binary value. So again, how many degrees of shift indicates what we're moving to. So we're storing a lot of information and we're storing it across all of these different subcarriers, sending this information across. So we can send a lot more data, even at the binary level. Remember, the binary level gave us 1 megabit per second with DSSS, but our most basic binary level only gives us 6 megabits per second when we use OFDM. As we use more of our sub-channels, right, we're able to occupy all of our sub-channels. We can move up to 9 megabits per second. When we move to the 4 different phases, right, the quadrature mode, we go to 12 or 18 megabits per second. So we're doing better than DSSS already, but we can get better. We get better by using quadrature amplitude modulation. See, everything we've been measuring so far is adjusting the phase of the frequency of the waveform that's being sent out. But what we could also now do is adjust the amplitude. So if the phase goes up and is adjusted 90 degrees, then that might mean this guy right here. If we adjust it 270 degrees and the amplitude is going down, well, then that would be a guy over here. All right, so we've got our different adjustments that are being made for amplitude, and we can actually adjust amplitude in 4 different positions. So amplitude is adjusted at the high swing, at the low swing, not at all, both. It's got the ability to measure all 4 of those. So double high and low, nothing. 1 high, one just normal. Both of them extended out. So those 4 different positions then gives you 16 possible values that are presented right here. So therefore, we got 4 bits per wave, all right, per wave. Very powerful stuff. And again, that's going to give us even higher degrees of data throughput that can be sent using this method of modulation.